Today we're going to get a bit more specific about the concept of limits in calculus. And whenever we talk about limits, it's a very precise thing. It's the limit of a function at a point. And to give you a bit more intuition, I want to show you two functions, f and g. And I want you to note that if I get arbitrarily close to a, so here's a point x, and it's very close to a. Notice that f of x, here's x, here's a point x, and f of x is very close to L. Here's my value f of x, and here is my L, which happens to be f of a. Now let's look at this function. Well, here's my f of a, or g of a. Alright. But notice that there are values which are arbitrarily close to a. Here's my value x. And here's my g of x. And it's very far away from g of a. Right? See this distance? That is g of a minus g of x. So in this case, we say that the limit of g as x approaches a doesn't exist. And in this case, the limit does exist. So here, the limit as x approaches a of f of x happens to equal f of a. And in this case, the limit as x approaches a of g of x does not exist. Let's look at another example. I want you to compare these two functions. Notice that when we approach a here from the left, the function values are approaching f of a. This is my function f. Let's call this function h. However, if we approach a from x from this direction, notice that the value is going to infinity. So these are two different ways that limits don't exist. Here, I've got good behavior coming in from the right. So in this situation, we say the right-hand limit exists. And in fact, the left-hand limit also exists, because as x approaches a from the right, the function value is getting close to some value. What value is it? Exactly this value, whatever it is. So the right-hand limit exists and the left-hand limit exists. Sorry, from here this was the left-hand limit, and from here this is the right-hand limit. Here, the left-hand limit exists, but the right-hand limit does not exist. So that's just some intuition about limits. What's the definition? We say that the limit of f as x approaches a exists if given epsilon greater than 0, there exists delta greater than 0 such that x minus a is less than delta implies that f of x minus L is less than epsilon for some given L. So in other words, L is the limit. Now that's really quite a mouthful. It's a very sophisticated concept, but the examples that I've shown you should really give you intuition into what a limit is. Now, limits have properties, which will be very useful in doing computations. We prove them using the definitions, but I won't prove them for you now. And we'll only talk about a few properties. So suppose that the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m. Then the limit as x approaches a of f of x plus g of x equals L plus m. Okay, that is the addition property of limits. And I'll just state one more, which is the limit as x approaches a of k of f of x, where k is some constant, equals k times the limit as x approaches a of f of x. So to give you some simple examples, suppose the limit as x approaches a of f of x equals 5, the limit as x approaches a of g of x equals 8, then the limit as x approaches a of f of x plus g of x equals 13. Okay, and a could have been anything in this scenario. Another example, let's say the limit as x approaches 0 of f of x is 5. Then the limit as x approaches 0 of 2 times f of x equals 2 times the limit as x approaches 0 of f of x equals 2 times 5. Limits are really useful when discussing difference quotients. So, as an example, limit as x goes to 2 of x squared minus 4 over x minus 2. Notice you can't put 2 directly in here or else you'll get 0. So the only way to really understand what's going on with this difference quotient is via a limit. So I factor the numerator and remember, this limit idea means that x is close to 2, but x is not equal to 2. So therefore, this is not equal to 0, this is not equal to 0, and I can cancel. And now I can just evaluate. As x approaches 2, this value approaches 4. On the other hand, let's look at the limit as x approaches 0 of 1 over x. Now, you know what 1 over x looks like. It is this function. And there's nothing I can do to this algebraically, this function, to make, to cancel the 0 or the x in the denominator with something in the numerator. This limit clearly doesn't exist, because as I get close to 0, from the right, the function goes to infinity, from the left, negative infinity. So that equals does not exist. And more specifically, I put the plus here to indicate from the right. The limit as x goes to 0 from the right is infinity, and the limit as x goes to 0 from the left is negative infinity.